So this is a new learning resource talking about generating text with ARN and ANDs. We used to cover this unit as a actual project in like Unit 10 in a future unit. But what we're seeing now is this recurrent neural networks have largely been replaced by some newer models. So I moved this into this learning module here so you can go through it. We can kind of talk about it and see the basis because this forms the basis for most of the new large language models and things like that. So I'm going to start by just going through this learning activity here and walking through that. So again, this used to be a project here that we used to do for generating text, and so the video here might actually walk through and talk about it as a project with a write-up, but we're no longer treating it that way. So instead, we're just going to walk through and talk about it. So again, we're importing our libraries here that we're working with. So we import our libraries. There's a couple new things we're importing. There's a tokenizer we'll see and some stuff like that, some new layers here, including the LSTM and GRU layers. This is also set up to use TPUs here, and you have to have some special code to do that. We don't actually have to do that here, but there is, you used to have to set this up to run on TPUs, make use of them on this. So we can just ignore that. Okay, so first we're going to look at generating text with recurrent neural networks. We're going to import some text. I have a couple public domain texts out there: Alice in Wonderland, the Bible, I think this is King James Version, and the Wizard of Oz here. So we import these. There's also some Shakespeare here. So there are these different variables that hold the URLs of these different locations, and then you can select which one you want. So if you want to do Alice in Wonderland, you would just take that and make sure the URL is set to the Wonderland URL, or if you want to do the Bible URL. So that'll be whatever URL we're going to use, and we'll bring in that text here. And it will create a variable called sample text, which will be, in this case, just the first 200 characters in the text. But later on, we'll read more from that text. So that'll download and bring. Now, we're going to have to work with this text. And so the question is, neural networks need numbers. We need activation values for our nodes, input nodes. So how do we store words or text in there? So one way we're going to look at, and this is the first way, is to just do a character-based system here. So we can look at the word like Gibbons, and then we can just assign every letter a different number, a token. So G could be like 19, I could be 9, B could be 21, and another B could be 21. So we'll just assign it. Now, there are some standard ways of doing this, some like ASCII or Unicode, but we often just assign kind of random tokens because we don't need that many. We just need whatever letters are in our sample text for this. So here we actually send how many distinct characters. There are 39 different kinds of characters in the text, and we're assigning some random numbers or letters to these texts. So we use a tokenizer to do that for us. Once we have this done, tokenizer, we're going to break this text into small windows. And so again, I'm not going to go through this code too much, but we're going to do windows of 100 characters. And so what we do here is we look at text, and we're going to try to predict the next character in a text. So we'll look at 100 characters in a row as the input, and then the output will be to predict the next character in the sequence. And then we'll step forward and look at the next 100 characters and predict one there. So we kind of have this sliding window of 100 characters that we'll use for inputs, and we'll just slide this window along, grabbing each window of 100 characters, and always then be trying to predict the next character in the sequence. So that's what this code kind of does, is set up these inputs. Now this is our RNN. We set up a sequential model. We do LSTM. Here we're doing 2 LSTM layers for this, and then a kind of a flat layer. This is called a time distributed layer. I'm not going to go into too much detail for how that's different than normal, but it's a wrapper around a dense layer for this. here. And again, because a lot of this is being replaced now with new models, but just this is a stack of two LSTMs plus a dense layer basically for that. And so it shows LSTM, LSTM, and then this dense layer. There's only 62,000 parameters in this model, relatively small model. And then we do some pre-processing for our text. We're going to give it some initial text. How are you, Y, O, and then have it predict the next characters in this sequence here. So again, we have some methods here that'll be figuring out the next text character, predicting the next character, and then doing that. Again, what we generally have to do is we take text, we have to tokenize it into numbers. The model will then predict a number, and then we have to take that and use again our tokenizer, convert that into a character again, and process that back. So some of that stuff is done in these models. So here we're setting up our next text. We're feeding it how are you to our model, and then we're predicting things. So we're running this and predicting different text, and then here's what we get out. It predicts an E and then a space and a T, E, space, E. So it's not doing really well. It's not even really forming words. It's doing some thes and some he's, but some ties. So it has some words in here, but a lot of this is not really words or stuff like that. So it's having some problems doing that. Now, if we train it some more, I think here's another example. This was trained on Alice in Wonderland, and it's doing better. It says, it generates the space rabbit, space some, space the rabbit. It kind of gets caught with the rabbit a little bit in a loop. The door a little bit. So at least it's generating one character at a time. At least it's forming words as spaces in between it. So it's learning some of the structure of the English language simply by looking at the text here. Now, normally we would go through, if this was a project and we modify this, we maybe try different network structures here, maybe different learning size windows for this. I'm going to just go back up here. Where's our model here? I missed it, I guess. It's such a short model here. Maybe use GRU, gated recurrent networks, instead of LSTMs, or different values here. So again, we can work on some different models here. But again, I'm not going to do too much of that today, because again, we're going to skip over a lot of this because we're going to move on to the new models. So section 3 takes a different approach. Rather than encode each character, we're going to encode each word here. So again, we're going to work with our given texts here. We're going to decide which one we want to use. Now we're using Wonderland, Alice in Wonderland text here. We're going to read that in. Here's some sample text of that. We're going to create a new tokenizer, and we're going to tokenize each word of this stuff. So the number of words, and again, typical vocabulary a person might have maybe like 20,000, 50,000 words, 100,000 words. So a lot, and that's hard for us to process with this size model. So we're going to limit it to the 2,000 most common words. So we're going to start to just look at the 2,000 words. So we're going to feed that limit into the tokenizer. So it'll assign numbers to the 2,000 most common words, and it'll assign a separate token for every other word for that. So here's like the most common word is the. It's assigned a token of 1. And is assigned the token of 3. 2 is 4. And you can see this is kind of Alice in Wonderland, because Alice is assigned a token of 10th. It's the 10th most common word here. Now there's some weird ones here, like the single quote is actually treated as a word, and it's here. So some things like that are treated, are kind of strange, but that's how the tokenizer works. And so here's like a sentence is a whole group of tokens in a row. So this is how we convert like a sentence into a word of tokens with this tokenizer. Each word is assigned a different number. And again, with us, it's a number between 0 and 2,000 because we're encoding 2,000 unique words in this. So now our input will be 2,000 and a vector of 2,000 numbers, because we're going to use one hot encoding for this. So again, remember, one hot encoding, we have a bunch of zeros, one for every possible value, and then one of the positions will be a 1 here. So token 1, so the word the will be encoded this way. A 1 and then a bunch of zeros after this. Where token 2 or word number 2 will be encoded this way. A bunch of zeros, but a 1 in the second spot. Again, so each one of these will be 2,000 zeros where 1 is hot. One position will be a 1. So this is called one hot encoding for this. So our input is 2,000 attributes or values long. So that'll be our first thing. And then our output size, we had to predict a next token. So our output size will be similarly like that. We're going to feed in strings of 10 words at a time. So this sets up and feeds in, creates a database. So we'll look at 10 words and predict the next word in the sequence. So this is kind of the what our input is look like. It'll be again 2,000 values, one hot encoding. So this is each word. So this is the first word in the sentence, the second word in the second, the third, and there'll be 10 words in the second sentence. And then we will predict the output we want to predict is the next word, the 11th word in the sequence. There. Now these all show as zeros because again there's only one hot one in each of these, and there's 2,000 of them, so there's a bunch of them we're not seeing here for that. So the input sequence is 10 character or 10 words, and the output is one word. So now we set up our LSTM here for it. And here we're doing some dropouts, some LSTM, and then feeding it to a dense layer and a softmax layer when we're done trying to predict our words. So this is kind of our structure here. So again, the final output is a 2,000 word vector because there's 2,000 possible words. And so we're trying to predict the next word in sequence. So again, this is getting a little larger, 3 million parameters for this, so we can fit and run this. This takes a while to train. Now, one of the problems with these recurrent neural networks is they don't parallelize very well. They run very slow on our system. So even running these on like a GPU or a TPU won't help much because the way recurrent networks are done is you have to completely calculate one before you can calculate the next step, where with like convolutional neural networks you can do a lot of things in parallel and feed them through and parallelize things a lot. So you can make use of the many processors like in a GPU to do many pixel calculations at the same time, but that's not the thing here. So each training here takes more than like 2 minutes for each of these. So this takes a long time to run. So, okay, now we're going to actually generate some words. And again, I'm not going to walk through this, but again, this is going to take a word, a sequence of words, feed it into our system, and then we're going to when it predicts a word, we're going to add that to our input and use it to predict the next word, add that to the next predicted word, add it to our input, and use that to predict a new word. So here's what it's predicting, some examples of the output. So with the stick, but the march of all in a large voice, and you like the way. So again, it's getting some phrases, the way out of a moment, I can't want to play. So some of this is okay. It's seeing some long-term dependencies here. I mean, but it's not doing great. It's certainly no chat GPT at this point. But again, this was kind of state of the art in like 2017 time frame, was this kind of words until we got that. So that just shows you how, and again, we're generating each word at a time. There's 2,000 different words in the vocabulary for this, and it's just trying to predict. And so it'll look at this sequence of words and try to predict what the next sequence is. But again, it tends to not pay attention way back in time, but just at the last word or two. So often the word it predicts fits pretty well with the last word or two, but not for the whole sentence, as we see. Okay, so that's this model there. And again, you're saying, well, why is he teaching us this if it's not used anymore? Well, it is served as a basis for something called transformer models and attention. And those grew out of those models. So you can see from those models, again, they didn't work very well. They only paid attention to the last couple words. And often with a sentence, you had to really pay attention to certain words to see every other word in there. So when we're working with that, we want to talk about the attention mechanism here. So here's a couple articles about the attention mechanism. And this was introduced about, again, we've been working with different attention mechanisms, since the 90s. I remember when I did my PhD, I was working with one type of attention mechanism, but it just did not work very well. Around 2015, we got this kind of attention mechanism that started getting more popular, and we're going to look at that. So here's one view of the attention mechanism. So again, this is using attention with recurrent neural networks and long short-term memory still here. And so this actually did improve their performance. So again, this provides a good overview of recursive neural networks, how you have an input, you have some hidden layer, and there's a recurrent network connection back to that layer, and then you go to some output. And then they show some ways of that, or how you can look at stacking these together. Now, one thing to watch when you see these stacks going forward is that they're either showing different versions in time, or they're showing a whole sequence of these modules together. In the future, we'll start putting a whole sequence of these modules together, but this is actually a single model, this model, but we kind of unwrap it. So it shows it at time 0, time 1, time 2, time 3. So at time 1, we send the input into this model, but it's also getting the activation from the hidden layer from time 0. So that's what this arrow shows. And then we're calculating the output at time 1. So this is time 1. And then at time 2, this is the same, this network at time 2. And we're showing this is kind of like a sequence of frames in a movie. This is one frame, this is another frame, this is another frame at different times, and things are just changing. So that's what this model is showing here. Okay, there's some different views. I'm just going to scroll down to the end. Again, this actually walks through how these long short-term memory networks work, and talks about different activation functions we could use there and how this works. We're not going to go over it again because a lot of these are kind of falling out of favor now, so we're going to skip over some of these here. Now, what this model I will show you is not actually necessarily a time one, but this is going to show you an encoder-decoder sequence where we'll have multiple networks here stacked together, and we still have the output of one feeding to the next one, but we won't necessarily have an output there, and then we'll have a decoder. So what we'll feed in is we'll feed in multiple inputs at the same time. So there's not a time necessarily here. These are the 4 words all being fed into this sequence at once. And we encode it in a certain way, and that encoding will be fed up here, and then we'll decode that sentence. So we'll look more at this encoder-decoder sequence in next week for this. But we're going to add an attention mechanism to this. So how we're going to do an attention mechanism to this, and what does that mean? So I'm going to kind of skip over this, but if we have a sequence of words going into this, we're going to try to figure out which of these words are most important for predicting the next character or next word in our output sequence. Here. So we're going to encode multiple words in a sentence and then do some summing here. And again, I'm not going to go into details, but just say there's some attention mechanism. We're going to try to do some weights and summing to figure out how important these words are to predicting this next word in the sequence. Okay, so this is kind of how things are going to be set up. We'll have a set of encoding networks here. In this case, 4 different networks getting 4 sequential words fed into it. That'll be fed into this attention mechanism here, which will again do some sort of sum and try to figure out how important these words are. And that attention stuff will be fed to these decoders, as will these words be fed here, and the decoders will try to decode the sentence. So often what is used like is for machine translation. So we may feed a sentence in here in English, 1 word at a time, and then a output might be a sentence in Spanish, or French here. And it's important when you're translating some words, when you're looking at the translation here, yeah, it'll be important to look at certain words in the input sequence. And it's not just a one-to-one. You don't always look at the third word, doesn't always just look at the third word in the English sentence, doesn't necessarily match the third word of the French sentence. So we'll figure out which ones are most important here. So again, this kind of shows some of these sets of LSTMs fed forward into this system. We'll get more into this next week, but I just want to kind of motivate your ideas here. And here's kind of an example. So this is a sentence, I think in English. The agreement on the European Economic Area was signed in August 1992, and this is the it translated for us. So this is the French translation. And so some of these, it's a nice direct. So the matches the agreement and accord. So if we're going to translate those two words are pretty well direct match. But there are some places where we don't have a direct match. European Economic Area, if we're translating that to French, we'll translate that into zone economic European. So the wording order changes. So this is trying to show that this word European, which is the, fourth word, really helps. We need that when we're trying to generate this word here. So this is an important word for generating this word in the output sentence. And this is another way. So this is just kind of a heat map showing which words are important when, and so anything you see that's not on the diagonal here means that when we're trying to do this or calculate this word, that this is an important word as far as this goes. So importantly, we need, if we're going to sign something or an agreement, we need the verb. We need to kind of know the noun associated with that verb for that. Okay, I'm going to jump. I'm not going to go too much into this other attention model, but this actually provides a little more detail of the attention model. So I'm just going to show you. So again, we have these encoder decoder networks. Here we're feeding in, I think, a Spanish sentence. We're feeding a couple words of that. We have some hidden state, and we have the output. So again, these are LSTM modules here, 3 modules in a row, and these are LSTM modules here, multiple modules connected together, generating the output layer, and then some hidden state here. Encoder decoder, and we'll see more of this in the future. But for this to work, so again, they're showing how each word in a sentence is fed into these modules, and we have some hidden state there. But again, we're going to look at this attention module here, where we feed in something into an encoder, we have an attention model, and then it goes to the decoder and we get some another image. So sometimes we'll be doing words or images to images, images to words, words to words, stuff like that in these models. And again, same sort of match for the attention or heat map there. This talk starts talking about self-attention, and we'll look at that. So far our attention model was just looking at the attention, what words in the output or the input are needed to predict each word in the output. But here we'll actually look at which words in the input are used to understand the rest of the input here. And we'll look at, in the future, BERT, a bidirectional encoder representation for transformers model here. So, okay, so let's see. Yeah, I'm not going to go too much more into the self-attention for now, but it's you can look through this. We'll spend a fair amount of time on this stuff in future units. So again, attention was important, and that was added to these recurrent networks to make them better. But then we learned that attention is all you really need. You don't actually need the recurrent network so much, the LSTMs and stuff like that. So there's a seminal paper that came out in 2017 that was titled "Attention is All You Need," and this defined this new transformer architecture. And so things like GPT, generative pre-trained transformers, those are transformer models, and this paper defined that whole model. And so in the future, we'll be looking a lot more at transformers rather than these recurrent and LSTM networks. But again, they're based on the encoder decoder models, which use these LSTMs and RNNs and stuff like that. So next week we'll look more at encoder decoder models and attention, and then we'll build towards the transformer models. Okay, hope that helped.